All right, in this question, Nate is hitting a tennis ball. He's serving a tennis ball. He does it horizontally. So you can see the green arrow in this example. Unlike the previous example, the green arrow is directed completely horizontally. So whatever speed he's launching it is going only in the horizontal direction. So one of the first things I hope that you can sort of take away from this idea is that when you hit the ball initially horizontally, that implies that the vertical velocity initially is zero, because all of the component is projecting it horizontally. If you look at that green arrow, before in the Justin problem, we were able to add a purple and a green vector to show the components. In this example with Nate, there is no components because it's all directed horizontally, or another way you could say that is the horizontal is the component. Okay, so moving on, the idea is that Nate, the first question is asking us what minimum speed does he need to clear the net. And they're telling us that the net itself is so this net is 0.9 meters. Let's just zoom in here. 0.9 meters above the ground. Nate is hitting the ball 2.5 meters above the ground. So the idea being that we want to know the difference. And we can do that math and we can see that it is 1.6 meters. So the ball's going to drop 1.6 meters on its way to the net. If it drops more than that, he doesn't clear the net. I mean, he can drop less than that. But let's just take that as the sort of the value that it's going to drop. So I can put in 1.6 meters here. And this is where I want you to be super careful with your sign convention. Remember, in the vertical, we have acceleration, g, and let's make down the negative direction and up the positive direction. If the ball ends up 1.6 meters down from where it started, that implies it has a negative displacement, right? So let's put a negative sign in there. We know this acceleration is negative 9.8 meters per second squared. So you can see already I've got three pieces of information. I have the delta y, I have the initial vertical velocity, and I have the acceleration. The question is asking us the minimum speed. So really what the question is asking us for is this. This is my question mark. What minimum speed is required to hit the ball? We know the ball is being hit horizontally, so they're asking us for the horizontal. So we need that. Now we also know from the question that the net is 15 meters away from Nate where he's standing. So if we knew the time, we could find this. So as you know, we can figure out the time here, and it's the same time as here. So we plug that in there, and then we have what we need to do. And in this case, my final velocity is my don't know, don't care. All right, so let's do this. We've got in the vertical, let's do it down here. We're going to use this equation, delta y equals VOY delta t plus 1/2 a delta t squared. That's the equation without final velocity. So we'll plug in the numbers. Negative 1.6 equals, this is 0, right? So that's just 0. 1/2 a is negative 4.9 t squared. Okay? So now we can just solve for t. These negatives cancel out. Don't do funny things with your signs. If they don't work out, you probably ignored your sign convention. That's a good chance for you to go back and say, oh, I forgot my sign convention. Let me be a little more intentional about this. So 1.6 divided by 4.9 and take the square root of that. We're going to get 0.5714. So, sorry, let's just do this. So when I solve for t squared, I get 0.3265, and then I'm going to take the square root of both sides, and I get t equals 0.5714. I'm just adding extra digits, 5714. Okay, now I'm going to add that in here, 0.5714. I have two pieces of information. Now I can find Vx equals delta x over delta t, and that equals 15 meters divided by 0.5714 seconds. And our answer is 15 divided by, that is 26.25, 26.25 meters per second, and that's the answer. So if Nate hits the ball with a velocity of 26.25 meters per second, he will just clear the net. If he hits it a little harder, he will clear the net with a little more, it'll go a little higher. If he hits it a little lower, it's going to hit the net. So this is his minimum speed he wants. There's other factors in tennis, obviously. If you hit it too hard, you're going to end up hitting it over here somewhere. And that's what question 2 is, part B is about. If he does hit it at this speed, is his serve good? In other words, does it land in this 7 meter, does it land within this point? And so we have to figure out what we need to put in here. So I'm asking you these questions. What variable is this question asking for? Is it one of the above or a different one? And do you need to find the answer? So what do you need to find the answer? So let's just write our variables again, because I kind of want you to get in that habit. Delta y, so this is the vertical and the horizontal. I'm looking for this on the test. I'm looking for you to write out your variables. Delta t, v naught, v a, and this is y's, right? These are in the vertical. Horizontal is delta x, delta t, vx. Okay, so what do we know here? Well, right away I can see that I have a different delta y. In the first part of the question, it only had to clear the net. So I only had to travel this distance, right? But in the second part of the question, I actually want it to get it's got to end up here, so it's got to travel the rest of the way down. So in part B, that's weird. In part B, I'm actually gonna put the full negative, this equals negative 2.5 meters. It's going the whole distance down. Gravity is still the same, negative 9.8 meters per second. The initial speed is still the same. It's still 0 because when you look at it, it's still the same initial conditions, but now we're just extending our problem a little bit farther. So we're gonna approach this second part of the problem in much the same way we did the first part, only now we have a bigger distance. So we also have some other information like this 15, we have information like 15 and 7. Do we put in the fact that this means 22 meters, right? The total distance of the court is 22 meters. Do we add that in here? Do we say 22 meters goes here? And this is one of the things I want you to really sort of understand in these problems. Sometimes what you're doing is saying, what we really want to know here is how far does the ball go? So really what this is my question mark. This x is my question mark. And what I want to do is find that number and compare it to the 22 and say, is it greater than or less than 22? If it's greater than 22, the ball's not good. If it's less than 22, the ball's good, right? We also know the same, we've been told it's the same Vx from the previous problem. So this is gonna be 26.25 meters per second. All right, so do you see the path through this problem now? We're going to use these three pieces of information to find delta t, knowing that my Vx again is my don't know, don't care. We're gonna plug this in again, and except this time we're gonna find delta x instead of delta t. So let's do that. And now let's see. So again, it's a slightly different problem, but it's similar. We can say the same delta y equals v o y delta t plus 1/2 a delta t squared. Same thing, my v naught y is still 0 because of this, but now my delta y is negative 2.5, and that equals negative 4.9 t squared. We'll fast forward this a bit and get t equals, oops, turn on 2.5 divided by 4.9, take the square root. We get 0.714, 0.714 seconds. Plugging that in here, now we can find delta x equals, so I'm gonna plug that in here. Let me do it in this color. 0.714, and then we get this equals Vx delta t, which equals 26.25 times 0.714. Plug all that in, and we get 26.25, 18.75. Okay, so now delta x. We look at the number. So is this greater than or less than 22? We already know it cleared the net from part A. So since 18.75 meters is less than 22, the whole length of the court, the serve is good. Of course it's good. Nate served it. The serve is good. Okay, hope that helps.